What if I told you that in order to perfectly design the heating system in a modern home, engineers literally have to invent imaginary water?
I mean, it sounds crazy, right? But it's true.
Yeah. Today on the deep dive, we're looking at the invisible kind of mind-bending math that actually dictates your monthly utility bill.
Exactly.
We're pulling from this incredibly detailed engineering document. It's basically a master curriculum outlining the precise calculations for autonomous heat pump systems. And our mission today is to decode the complex thermodynamics going on inside your walls.
Right, showing you exactly how engineers balance physics, human comfort, and, well, hard economics to lower your energy footprint.
Yeah. And, why should you care about this?
Well, whether you're actively renovating or maybe you're dreaming of building an off-grid cabin, or you just appreciate understanding the hidden mechanical layers of the world around you.
The hidden stuff is the best part.
It really is. And these formulas, they completely change how you view your own home. Because the decisions made before a single pipe is even laid, they basically dictate your operational costs for the next 30 years.
30 years.
Yeah.
That's a huge commitment. So, okay, we have to start with the foundational math here. Before anyone even opens a catalog to look at shiny new heat pumps, the engineers require a calculation of the project heat load.
Right, the master equation.
Yeah, formula 6.1 in the document. And I look at this formula like a corporate budget, basically. A home isn't just one big heater. According to this master equation, it had three separate departments, let's call them, competing for the energy budget.
Right, so you have space heating, domestic hot water, and then attached systems like ventilation.
Exactly.
And the space heating is where you see the most variance, by far. I mean, this is the raw energy required to counteract the heat. Your house just naturally bleeds into the winter air. And what the engineering document makes crystal clear is that you don't just calculate the volume of air inside the rooms, you have to factor in the physical composition of the structure itself using these specific load factors.
Okay, let's unpack this because this detail stood out to me immediately. The document states that tall buildings with heavy concrete ceilings get a load factor of 0.90 applied to their calculation.
Right.
But low buildings with light walls, like, suspended ceilings, they get a factor of 1. So wait. Just by living in a heavy concrete structure, the math instantly gives you a 10% discount on your heating requirements.
Yeah, a flat 10% discount. And what's fascinating here is the underlying mechanism, which is thermal mass. It physically alters the operational cycle of your heating equipment.
How so?
Well, heavy materials like concrete or stone, they absorb heat really slowly and they hold on to it. They essentially act as a massive thermal battery for your house.
Oh, wow.
So when the ambient air temperature drops and your heat pump cycles off, that concrete ceiling begins radiating its stored energy back into the living space.
It's like a delayed reaction.
Exactly. It physically delays the moment your thermostat registers a drop in temperature and calls for heat again. But a timber and drywall house, that has almost zero thermal mass.
So the heat just vanishes.
Right. The moment the heat turns off, the air cools rapidly. So that 0.90 discount, it accounts for the fact that the building's own mass is basically doing part of the heat pump's job.
That is wild.
Yeah.
And, if the building material alters the math by 10%, the insulation just completely rewrites it.
Oh, absolutely.
Because the source material details the specific heat consumption based on insulation quality, right? Measured in watts per square meter.
Yes.
So old houses without special insulation, they're bleeding like 120 watts per square meter. A standard home uses about 80. But a new build with high-quality insulation drops all the way to 50.
And ultra-low energy homes hit 40.
40, that's a massive drop.
It's a 2/3 reduction in energy demand just through passive materials, which, dictates the golden rule of thermal engineering here. Critical thinking dictates you must always slash the space heating load first before sizing the mechanical equipment.
Right. Don't buy a massive heater for a leaky house.
Exactly. Because if you skip the insulation phase and just buy this massive heat pump to compensate for 120 watts per square meter of heat loss, you are fundamentally over-engineering the mechanics to fight a losing battle against physics.
You're just paying to heat the neighborhood, basically.
Literally. You'll be spending thousands of dollars on electrical consumption for no reason.
Okay, so we add the modern insulation, which successfully minimized the space heating department's budget.
Yep.
The next massive energy draw in Formula 6.1 is domestic hot water. And reading through the engineering docs dealing with a hot water load forces a major strategic choice onto you as the homeowner.
Yeah, two very distinct paths emerge in the source material here. You've got maximum accumulation versus partial accumulation,
Wow.
and they both dictate entirely different mechanical setups and, well, daily operations.
Here's where it gets really interesting to me. Maximum accumulation is clearly geared toward homes taking advantage of a two-rate electricity tariff, right? Like cheap power at night, expensive power during the day.
Exactly.
So the strategy demands a massive buffer tank designed to hold double your average daily consumption. And the baseline metric they use is 25 to 50 cubic decimeters or liters per person, heated to 60 degrees Celsius.
Right.
So the heat pump fires up during those cheap nighttime hours, works intensely to heat this massive volume of water, and then shuts off. And it leaves you to basically coast on that stored hot water all day long.
Yeah. And then partial accumulation flips that entire logic.
Okay.
It relies on the heat pump running constantly to prepare water on demand throughout the entire day. So you install a much smaller tank based purely on your standard average daily consumption.
Though the source does throw in a funny little warning there.
Oh, about the bathtubs.
Yeah. It notes you have to manually increase this baseline calculation if the house has large soaking bathtubs. You can't cheat the raw volume of a giant tub, you know?
You really can't. The math will catch up with you.
Right. But looking at these two strategies, it feels exactly like the economics of grocery shopping.
How do you mean?
Well, maximum accumulation is like driving to a wholesale warehouse store at midnight because the inventory is 50% off. But to make that trip worth it, you have to buy a massive extra chest freezer to store all that food in your garage.
Right, right.
And partial accumulation is like running down to the corner store whenever you need a single egg. It takes way less storage space in your kitchen, but you are paying a huge premium on the unit price every single time you walk through the door.
That's a perfect analogy. You're hitting on the classic tension between capital expenditure, or CapEx, and operational expenditure, OpEx.
CapEx versus OpEx.
Right. So the warehouse strategy, maximum accumulation, that requires significant upfront CapEx. I mean, a tank large enough to hold double the daily water supply for an entire family takes up serious physical real estate in a utility room.
Yeah, it's huge.
It's heavy, it requires reinforced flooring, and it's just expensive to purchase. But the corner store strategy saves you that upfront CapEx and physical space, but it locks you into a higher OpEx. You're paying daytime peak energy rates for the lifetime of the system.
Which really adds up. So to see if that grocery store strategy actually holds up mathematically, I dug into this case study provided in the document.
The Riven scenario.
Yes, the Riv reality check, I call it. So it's a 120 square meter new build in the city of Rivne, housing a family of 3. And what struck me immediately is the temperature differential the system has to fight.
Oh, it's brutal.
Yeah. Winter temperatures in Riven drop to negative 21 degrees Celsius. And the groundwater entering the house is sitting at a chilly 10 degrees. But the family wants that water heated up to 50 degrees.
Right. And establishing the raw baseline is straightforward enough. 3 people, 50 liters each. That means the house needs a base daily volume of 150 liters of hot water.
Okay, 150 liters.
But real-world physics introduces a complication that standard formulas often miss entirely.
Which is?
The hot water tank itself acts as a radiator. It's constantly leaking heat into the utility room.
Yes. And the document quantifies that leak at 0.015 kilowatt hours per liter daily. And okay, how the engineers solve for this thermal leak is the most elegant, wild workaround I've ever seen.
It really is.
Wait, so instead of creating a separate, complicated thermodynamic formula to account for the lost energy, they just mathematically pretend the tank needs to hold more physical water.
Yeah, it's brilliant in its simplicity because, heat loss depends on all these complex variables. The surface area of the tank, the ambient temperature of the room, the thickness of the insulation jacket.
Too many moving parts.
Right. So instead of bogging down the primary equation with all of those moving parts, the engineers calculate the total energy lost through the tank walls and just convert that energy back into an equivalent volume of water.
Imaginary water.
Exactly. In the Rivne scenario, the daily heat loss is equal to the exact amount of energy it takes to heat 38 liters of water. So they just add 38 imaginary liters to the physical 150-liter requirement.
That is a wild, genius workaround. It normalizes all the messy variables perfectly.
It really does.
So now the math dictates we need 188 liters. But the adjustments don't stop there, do they?
No, they don't.
Because the baseline 50-liter metric assumes you are heating water to 60 degrees Celsius. But this family only wants 50-degree water.
Right, which changes things.
Yeah, adjusting the math for that lower target temperature inflates the required tank size even further, pushing the requirement up to 235 liters. So to cover this safely, the engineer selects a 250-liter tank, which calculates out to storing 11.6 kilowatt hours of energy.
And then we must factor in the final department from our master equation, which is the ventilation load.
Oh, right.
So the document outlines a ventilation system moving 200 cubic meters of air per hour. Now, even with a highly efficient 70% recuperation system, which basically captures heat from the outgoing stale air and transfers it to the incoming fresh air, the ventilation still adds a 0.8 kilowatt load to the overall system requirement.
Okay, so with all those variables locked in,
Yeah.
the document runs the final math for both strategies, and the comparison is staggering to me.
Let's hear it.
If this family uses the maximum accumulation strategy,
Yeah.
The midnight warehouse shopper with the massive 250-liter tank,
Yeah.
the total required system load for the heat pump is only 8.5 kilowatts.
Right.
But if they go with the partial accumulation strategy, the corner store shopper with the tiny 100-liter tank, the system actually demands a 10.1 kilowatt total load to heat water on demand.
Yeah, it proves that buying a bigger tank actually allows you to buy a smaller, less powerful heat pump.
It works smarter, not harder.
Exactly. And the mechanics behind this are crucial for anyone buying a heat pump. By purchasing a larger physical tank, you're creating this massive thermal buffer, and it smooths out the peak demands on the hardware.
Which is good for the machine, right?
Oh, it's essential. Without a large buffer tank, every time someone washes their hands or turns on the dishwasher, a smaller heat pump has to aggressively fire up its compressor to heat water rapidly.
Right.
This leads to short cycling, where the compressor is turning on and off constantly, which is just terrible for the lifespan of the equipment.
It burns out the motor faster.
Exactly. But the 8.5 kilowatt heat pump paired with the large tank, it gets to turn on, run at a steady, highly efficient, low speed for several hours to slowly charge the tank and then just turn off.
Wow.
So you buy a smaller, less expensive, less powerful heat pump, but because it operates under optimal mechanical conditions, it likely outlasts the more powerful 10.1 kilowatt unit.
So it's really all about flattening the curve of energy demand inside your own utility closet.
Precise.
Okay, so we've solved the physics for a reasonably sized 120 square meter home on a normal winter day. But what happens when the scale increases and extreme weather completely breaks the mathematical efficiency of a standard heat pump?
Oh, yeah.
The source material pushes us to look at the long-term economic reality with a final massive case study.
And the parameters here shift dramatically. We're now looking at a 350 square meter house in Riven.
Huge house.
Yeah, and they're keeping the indoor temperature at a very cozy 20 degrees Celsius. So to handle this scale, the engineers deploy a bivalent system.
Right, a bivalent system. The document specifies a 7-kilowatt Buderus air-to-water heat pump operating at a 35-degree regime paired directly with a gas boiler.
Yep.
And it states this gas boiler operates at 106% efficiency.
And the economic calculation is then run over a 5-year period, factoring in a projected 10% increase in energy tariffs over that timeline.
Okay, wait, stop right there. 106% efficiency.
I know.
That literally breaks the laws of thermodynamics. I mean, how do you get more out than you put in? You cannot extract more energy out of a machine than the raw fuel you put into it. It sounds like a typo in the engineering curriculum.
This raises an important question, and it is the most common point of confusion in modern HVAC. But it doesn't break physics. It's really just an artifact of how we historically measure the efficiency of burning gas.
Okay, explain that.
For decades, traditional gas boilers vented their exhaust straight up the chimney. That exhaust is incredibly hot, and it's full of water vapor created during the combustion process.
Right.
The old efficiency rating scale, where the absolute theoretical maximum was set at 100%, only measured the sensible heat directly extracted from the flame. It completely ignored the energy trapped in the exhaust vapor because older systems couldn't catch it.
Ah, okay, so 100% wasn't actually all the energy in the gas. It was just all the energy we knew how to catch at the time.
Precisely. But modern condensing gas boilers, they change the game. They take that hot exhaust vapor and run it through a secondary heat exchanger.
Oh, wow.
The vapor hits the cold metal, condenses back into liquid water, and undergoes a phase change. And when water changes from a gas to a liquid, it releases a massive amount of hidden energy. which is known as latent heat.
Okay.
Because the baseline grading scale was locked in before this condensing technology existed, capturing that bonus latent heat pushes the mathematical rating over the traditional 100% mark, yielding that impossible-sounding 106%.
Okay, that makes perfect sense. It's a quirk of the grading scale. But that brings me to my second issue with this setup.
Which is?
Mixing a highly efficient, futuristic electric heat pump with a combustion gas boiler. It feels like buying a plug-in hybrid car today instead of committing to fully electric. Why not just go all in on the heat pump and ditch the fossil fuels entirely?
It comes back to the severe weather penalty on air source heat pumps. Think about the climate in Riven. For 90% of the winter, temperatures hover in a moderately cold range.
Yeah.
The 7-kilowatt heat pump handles that beautifully, extracting ambient heat from the air incredibly cheaply. But an air-to-water heat pump's efficiency curve drops off a cliff as the air gets colder.
Right, because there's less heat in the air.
Exactly. So when that brutal negative 21-degree cold snap hits, a 7-kilowatt pump cannot keep a 350-square-meter house warm.
So the alternative would be to buy a massive, 20-kilowatt heat pump just to handle the deep freeze.
And that is a terrible misallocation of CapEx. You would be buying a massive, expensive piece of industrial equipment that sits radically oversized and underutilized for 350 days a year, all to handle a 2-week deep freeze.
Oh, yeah. That's a huge waste of money.
It is. The bivalent system relies on a switchover logic. The smaller heat pump runs the show all winter until the exact temperature where its efficiency drops below a certain threshold. At that exact moment, the system automatically shuts down the heat pump and fires up the gas boiler, which easily and efficiently handles extreme cold.
So you avoid over-engineering your electric equipment for the worst-case scenario. And that ties perfectly into the 5-year financial model mentioned in the document, the 10% tariff increase. This bivalent setup isn't just about thermodynamic efficiency, is it? It's a financial hedge against utility markets.
Oh, entirely. If the regional electricity grid becomes strained and power prices spike, your system leans more heavily on the gas boiler.
Right.
If geopolitical issues cause natural gas prices to skyrocket, you drop the switchover point and force the electric heat pump to carry more of the load.
So you're effectively treating your utility room like a diversified investment portfolio.
Yeah.
By maintaining access to 2 distinct energy markets, you insulate your operational expenditures against volatility in either sector.
You really do.
That is amazing. So just to recap this incredible journey through the engineering math today, we started by looking at how the heavy concrete ceilings of your home physically alter the thermal lag of your heating cycle, giving you a literal math discount.
Yep.
We discovered the hidden genius of imaginary water, converting thermal leaks into equivalent volume to streamline the calculations.
A great trick.
We explored how a massive hot water tank mechanically protects your compressor from short cycling. And finally, we ended up looking at a bivalent system acting as a long-term financial hedge to beat compounding energy tariffs.
It truly bridges the gap between abstract thermodynamics and real-world economics.
It really makes you realize that your home is not a static object, it's a living machine. Every single decision, from the thickness of the insulation in your exterior walls to the cubic volume of the hot water tank in your basement, all the way down to the exact structure of your utility tariff, it all changes the mathematical DNA of the house.
Absolutely.
To truly understand a building, you have to look past the drywall and the geometry.
You do. And if we zoom out from the mathematical DNA of a single house, it raises a rather mind-bending concept to ponder about the future of our infrastructure.
Okay, I'm ready.
Let's assume everyone in a neighborhood builds their house perfectly according to these engineering principles. They all adopt the maximum accumulation strategy to slash their operational costs. They install giant 250-liter tanks, and they all sign up for the cheap nighttime electricity tariff that kicks in at midnight.
Oh, I see where this is going.
Yeah, if the entire grid is optimized this way, at exactly 12:00 a.m., every single heat pump in the entire city is going to turn on at the exact same second to start boiling massive volumes of water.
Wow.
The very tariff designed to incentivize off-peak usage will instantly create a massive new peak on the power grid. It could potentially overload the transformers.
That's a terrifying thought.
It suggests that the true energy-independent home of the future won't just calculate its own internal math. To prevent grid collapse, your home's algorithm will have to constantly negotiate its heating schedule with the entire city's energy grid in real time.
Literally bidding for power microsecond by microsecond.
Exactly.
So your house is acting as an automated stockbroker for electricity at 12:01 a.m. while you sleep.
It's the only way it works at scale.
That is wild. It turns out achieving a comfortable, mathematically perfect home requires a level of diagnostic precision that touches everything from the concrete in your ceiling to the power plant miles away. Thanks for joining us on this deep dive, and we'll see you next time.